Have you ever wondered how the alternating current from your wall outlet transforms into the steady direct current that powers nearly all your electronic gadgets? It is a fundamental process in electronics, crucial for everything from charging your phone to running complex computer systems. The direct current output voltage from a rectifier circuit is primarily determined by three key factors: the peak voltage of the alternating current input signal, the specific rectifier configuration you employ, and the intrinsic forward voltage characteristics of the diodes used within that circuit. Let us dive a bit deeper into why these elements are so critical. The input alternating current peak voltage represents the maximum amplitude of the alternating current waveform, which sets the absolute upper limit for the rectified voltage. Different rectifier types process this alternating current input in distinct ways. For instance, a half-wave rectifier uses only one half of the alternating current cycle, resulting in an average direct current voltage that is approximately 31.8% of the peak input voltage, minus the single diode forward voltage drop. A full-wave rectifier, whether it is a center-tapped or a bridge configuration, utilizes both halves of the alternating current cycle. This leads to a higher average direct current voltage, typically around 63.6% of the peak input voltage. However, a full-wave bridge rectifier, while efficient, incurs to diode forward voltage drops during each conduction cycle, whereas a center-tapped full-wave rectifier usually experiences only one. These diode voltage drops, typically around 0.7 volts for common silicon diodes, are subtracted from the peak voltage, as energy is lost when current flows through the diode. Beyond the basic rectification, the presence of a filter capacitor across the output dramatically impacts the direct current voltage. This capacitor stores charge during the peaks of the rectified waveform and discharges it when the voltage drops, effectively smoothing the pulsating direct current and raising its average value much closer to the peak rectified voltage. The larger the capacitor and the lighter the load drawing current from the circuit, the closer the direct current output voltage will get to the peak value. Conversely, a higher load current will cause the capacitor to discharge more rapidly, leading to a greater ripple and a lower average direct current output voltage. To practically estimate or calculate the direct current output, you first need to know the peak alternating current voltage from your source. Remember that alternating current sources are often specified by their root mean square voltage, so you will need to multiply this by root 2, approximately 1.414, to find the peak voltage. After determining the peak alternating current, you then apply the appropriate diode voltage drop or drops depending on your rectifier configuration. If you are using a filter capacitor, your approximate direct current output voltage will be near the peak rectified voltage minus the diode drops, adjusted for any residual ripple voltage. An important concept to grasp here is the ripple factor, which quantifies how much the direct current output voltage varies from its average value. A lower ripple factor signifies a much smoother, more stable direct current output. Additionally, many practical power supply designs incorporate a voltage regulator after the rectifier and filter stages. This dedicated component further stabilizes the direct current output voltage, making it virtually constant despite potential fluctuations in the alternating current input or changes in the current drawn by the load. This level of stability is absolutely crucial for sensitive electronic components that demand a very precise operating voltage. By carefully considering the input alternating current peak voltage, the chosen rectifier topology, the characteristics of the diodes, and the effectiveness of any filtering, you gain the precise understanding needed to predict and design the direct current output voltage. This foundational knowledge is essential for creating reliable power supplies that deliver the stable energy modern electronic components demand for optimal and consistent performance.